Okay, so thank you all for coming and welcome to the first lecture of CS 159, Special Topics in Machine Learning. The topic of this term is data-driven algorithm design. Oops. Okay, so just a few comments while we get started. As everyone is aware, we are currently in an unprecedented situation in our society right now due to the current pandemic. COVID-19 is a massive public health crisis, hence the current situation. Obviously, everyone at Caltech, the faculty and the staff, we hope everyone is staying safe, minimizing risk to yourself and to any vulnerable loved ones that you may live with. We will be converting the later lectures into more of a discussion session. Obviously, the main purpose is to discuss topics in the course, papers and algorithm ideas and whatnot. But if students should choose to want to use some of that discussion for broader issues, I'm happy to do so. The earlier lectures, the first 4 or 5, will be really focused to get people up to speed so that they can move towards a project proposal for their final project, which is the bulk of this class. So that's how this course will be structured. So the lecture protocol, just a few things for everyone to keep in mind. Zoom has the option to send private messages to other attendees of the conference call. For example, you can send a message from one student to another saying, "This professor is so boring." Keep in mind that when I'm recording a lecture on Zoom, and all private messages are actually in that recording. And so all the students in the class who are going to be watching this outside of the normal live lecture will see those recordings. So please do not send private messages to each other via Zoom chat. Because this is a web conferencing app, it is quite challenging with multiple people are talking at the same time. So by default, everyone is muted upon entering the conference call. There is a raise hand feature that I am sure most of you are familiar with, but just in case you're not, if you click on the participants panel at the bottom of the screen of the app, that creates a participants pane, and at the bottom of the participants pane is a raise hand button. If you do that, I will see you raise a hand, and at the appropriate time, I can call you to ask a question. You may either ask it by unmuting yourself if you want to have your voice recorded, or you can ask by sending me a chat message. And I'll have points in the course where I will be asking students if they have any questions. Okay, so some class details. I'm the instructor. My name is Yi-Song Yu. For those of you who don't know me, I study machine learning. I've been studying machine learning for about, I guess, 16 years now, or 15 years. We have 3 TAs in the class, 1 primary TA, 2 secondary TAs. The primary TA is Jialin. The 2 secondary TAs are Hao and Joe. We have a course website and a Piazza. Hopefully you're all registered on Piazza. Most of all the course announcements will be happening through Piazza from now on. If you have trouble finding these websites, the course website is linked to off my homepage. So if you just navigate to my homepage, it's easy to find the course website. And from the course website, you can find Piazza. Okay, so the style of this course. I know that some of you have taken CS 159 before and are taking it again. For those of you who haven't taken CS 159 before, the style of the course is a graduate level course. So the intention is to give students a broad overview of cutting edge research topics. And the students will dig deep into one topic for a final project, a research project, if you will. This class does assume that students are mature, so we won't be doing much hand-holding in terms of the topics. And the goal of the initial part of the course is to give you sort of a broad overview. And the students then are expected to sort of dive deep into a topic on their own, or excuse me, in a group, but mostly independently. Obviously, the professors and TAs are there to provide guidance and feedback. So the grading breakdown. So historically, the class has been graded on 20% presentation, 80% final project. In previous years, the presentation was a student lecture. So most of the lectures were done by students. Because of the current situation and inconsistencies in internet access and all those things, the TAs and I decided this year to switch to a blog post, and details of that will be coming out in the next week or so of how to do that. And so it'll be like a presentation, just a written presentation rather than a oral presentation. So that'll replace the presentation portion of the grade. The bulk of the grade is in the final project, and the final project has a report and a presentation, and we'll figure out the right way to do a presentation that makes sense. If it turns out that a presentation is not possible for logistical reasons, we'll find an alternative, perhaps a blog post as well. So as I said before, the first few lectures will be an overview of topics, and the remaining lectures will be a discussion of papers and advanced topics. And the later lectures will typically not be structured as lectures, perhaps as guided walkthroughs of papers, or if students have a topic or a paper they want us to discuss in the class, we can discuss that in the downstream lectures. They won't be as structured. Students will write blog posts discussing a topic in depth. We will actually provide links to skeleton code and other code that have been released on relevant topics of this course. And probably the easiest thing to do is to take that code and play around with it and maybe do a few extensions, do a few experiments, and then write a blog post about it as an in-depth exploration of a topic. The blog posts will be doing groups, and they will be due on Friday, April 24th, which is the end of the official 4th week of class. We are currently at the beginning of the 2nd week of class officially. So about 3 weeks from now. The final project is 80% of the grade. The final project can be on any topic related to the course. You should work in groups.
You sound muted.
Yes, there's a question, yes?
No, you just muted out for a little bit, at least for me. It's back right now.
Okay, sorry about that. Let me just repeat what I just said. So the final project can be on any project related to the course. You work in groups. The due dates, the proposal for the project is May 1st. It's not binding, excuse me. It's meant to just simply force you to have a concrete proposal, and then the TAs can provide feedback. Of course, the TAs can provide feedback before you submit the proposal as well, but we will certainly provide feedback on the proposal. Presentations are between June 3rd and 5th. Again, if it turns out that logistically this is challenging for students, we'll find an alternative, but this is the current plan. And for groups with a graduate student or a graduating senior whose term ends early in the spring, the final report is due June 6th. For groups that contain only non-graduating students, which are basically freshmen, sophomore, juniors, hopefully just sophomores and juniors in this class, the report is due a week later. So the focus of this course is to help you do a project in rigorous algorithm model design. This is math intensive, but nothing too hard. And we will walk through the relevant math in the class. Not this lecture, but in the subsequent lectures. And given an understanding, a working understanding of some algorithm, or hopefully multiple, but at least one algorithm in this class, apply it to something interesting that you might find interesting. So one question that students often have when taking a research course for the first time is, what does rigorous mean? Rigorous is about being able to clearly state your assumptions, formalize them, state how a model or approach you're developing exploits or satisfies those assumptions, and rigorously reason about the downstream implications of those design choices, sometimes with provable guarantees or assertions of correctness, but that's not strictly speaking required. You simply want to have a very sound reasoning that your model is a good one, starting from your beginning assumptions, which could be just of academic interest, or it could be inspired by a motivating application. What makes a good final project? There's sort of three categories. The first is pure theory. So study proof techniques, try to extend a proof applied to a new setting. The second is algorithms and models. Extend an existing algorithm or model or design a new one for a new setting. And the third one is an application. So you're really interested in some area. Perhaps you're a PhD student in, let's say, biochemistry. You want to study algorithm design for a certain biochemical application. And so how do we sort of figure out the right way to apply these methods to a new domain? So any type of topic, any one of these will make a good final project. Historically, most groups tend to do a mix of the second and third bullet points. Maybe some more on the second one, maybe more on the third, but historically a mix of the second and third. A few groups have done the first one. Some advice, don't limit yourself to the papers covered in lecture. The course website has a huge list of references, and the TAs will provide starting points for projects. That part of the course website is still under construction. It will be filled out by next week. You can use Colab, which is a resource provided publicly by Google to run some experiments. We'll have some Colab resources available as well. So finding groups. So most students taking this class will self-organize into groups. Having done the survey last week, I know that there are a significant number of students, a minority, but a significant number of students who are looking for groups and are looking for assistance in finding group members. And we will be brainstorming ways to help people match up into groups. That'll happen in the next week or so. If you have suggestions, please send me an email with any suggestions you might have. We are, in some sense, all into this together in terms of going to online classes, and this will present some challenges, perhaps unexpected. And so if you have suggestions, just send me an email. So at this time, I'd like to pause for any questions. If you have any questions, please raise your hand. Okay, moving on. So the rest of this first lecture will just basically present an overview of data-driven algorithm design, so just a high-level overview, an overview of possible applications, and basically it's going to help you decide if you want to take this class. I know that some students are still shopping around, not sure if they want to take the class, and so hopefully this first lecture will give you enough of a flavor of the topics that it'll help you make a decision. We may end a little early depending on how fast we go. So there are many real-world applications of data-driven algorithm design. So I'll start with some of the applications. So for example, string processing. If you work in biochemistry, you will do a lot of string processing, such as alignment, transcriptome assembly, folding, and many other things of that nature. And there are many things and many algorithms in these string processing applications that are currently designed by hand. And you can imagine using machine learning to automatically design parts of them or all of them. We have planning. So in planning, we have things like planning for missions like the Mars rover, planning for 3D printing. How do you plan a 3D printing path? Because planning for 3D printing is much more complicated than planning for 2D printing. Planning for conservation planning, and any other planning problem you can think of. They typically lead to what are called NP complete or NP hard problems. If you've taken CS 138, you should know what those are. Or 38, excuse me. And so many planning problems are NP hard, so people design heuristics to solve them well for specific domains, and we can imagine using learning to automatically design those heuristics. Engineering experiment design. So if you are designing some new kind of structure or chemical or even treatment of a patient, it typically, you do this optimization process where you run an experiment, you measure the outcome, from that you pick a new experiment to run, and that's sort of an optimization process, like an optimization algorithm. And so you can use learning to help accelerate or augment that process. More applications, including automatic theorem proving. Automatic theorem proving is useful for things like software verification, safety verification of flight systems and spacecrafts. Automatic theorem proving is useful for various other branches of mathematics where the proofs are just very complicated, but not particularly, perhaps not particularly insightful in terms of the low-level things. Auctions, so many complex auctions, also known as combinatorial auctions, are NP-hard or NP-complete, and so people use design heuristics to solve them well. Probabilistic inference, if you know about deep generative models, things like variational autoencoders, they're actually running an optimization algorithm at test time. Every time they see an example, they actually run an inference algorithm, which is solve an optimization problem, and they use learning to solve that. And so those are just a survey of examples. You may have your own. If you have questions about whether or not your problem is suitable, you can post a question on Piazza. We can have a list of possible algorithms, applications. And so this is just a sample. I'm sure we can collect more. So now the question is, okay, those are a bunch of applications where people are designing heuristics and algorithms to solve them by hand. Why might we want to do data-driven algorithm design? So here's a few places where it's quite natural to think about data-driven algorithm design. This is not an exhaustive list. So many solvers have tunable parameters. So you might have a solver and has like 30 flags, and the flags all have tunable parameters, like how much to weight this thing, how long to run this submodule, all that stuff to try to get this algorithm to run as quickly as possible on a huge problem instance. Some of these solvers have like over 100 parameters. And you can easily imagine that if you could just find the right parameters for this problem, the algorithm can run really fast. The solver can run really fast. But if you don't know how to tune the parameters properly, the solver can run quite slow. So we can use learning using data to try to predict what the parameters are. Many solvers rely on heuristics. So these heuristics include things like A-star search, where you need an admissible heuristic. Things like gradient descent with various sorts of momentum, where the momentum is typically heuristically designed to try to solve some optimization problem as quickly as possible. They may work well for one domain, but not for another. And if we just had a data set of representative problem instances of these types of optimization problems, perhaps we can learn a heuristic that's better than anything we can tune by hand, or at least much faster. Many solvers rely on key subroutines. For example, some solvers require a subroutine that identifies an important variable to prune next in a search algorithm. And you can actually use learning to design these subroutines. And so, given that these are places where we can do automated algorithm design from data, how do we use the data to automatically specify these? So these are just places where we can use data to specify. And so now the question is, how do we do that? And so there's sort of a checklist that we go through when we think about the most appropriate way of using data. So as many of you know, if you've taken CS 155 and 156, you can't just use data in any arbitrary way. You have to be thoughtful that the way you're using the data is actually solving your problem. And so that's going to be very important here, because we're going to be thinking about the ways of using data to solve a focused set of problems. Like, how do we train something about the solver so that the solver can use that and actually speed up the solving process? And so the high-level checklist is as follows. Do you have pre-collected problem instances? Are you collecting data on the fly? So I'll get into more details of what these mean in a second. Do you have pre-collected measurements? So it's not enough just to have problem instances, because you need to make a measurement of the problem instance. For example, I may need to run a solver on a problem and measure how fast that solver is on that problem. And collecting measurements in this sense is like collecting annotations for supervised learning. It's not enough just to have the problem instance. We also need the measurements. Are you learning a stateful or stateless model? Stateful models are ones that are being run throughout the solver process that take as input the solver's current state. So for example, if I'm doing a search algorithm, what's the current search tree of the solver? A stateless model is one that simply sets some global parameters of the solver and then the solver runs like a black box, and I don't actually look at the state of the solver. So just a few examples of, so here's an example that's pre-collected and stateful. So imagine that we are working with NASA and JPL. This is actually a research project that Jalin, my student Jalin, the head TA, has been working on for the last 4 years, possibly 5 years. Suppose we are working with JPL and we want to design algorithms that can help spacecrafts do faster planning. So a canonical example of this is a Mars rover that is trying to get from point A to point B safely. So this is an NP-hard or NP-complete combinatorial optimization problem. And imagine that we have a distribution of such planning problems. The distribution, for example, can be lifted from the historical data of the rovers, can be lifted from satellite imagery of Mars. So we have this distribution of obstacle courses of Mars, and that's pre-collected. That gets compiled into some sort of optimization problem. The details of that right block don't matter for now. It's just the details of some optimization problem. And we apply a learning to search algorithm. So we'll go into details of this kind of stuff later on in the course. But from that, we apply a learning to search, which learns a tree search heuristic. And then we apply a test instance. So a future instance, a new obstacle course on Mars, assuming that the training set that we've collected is representative of this test instance, then our learned heuristic should be able to solve the planning problem on this test instance much faster than the existing solver. That's the idea. And so the key idea is that we train a solver to solve an optimization problem well. We assume the training instances are representative. We apply the trained solver on test instances. And in this approach, because we have a lot of pre-collected training data, we can utilize data-hungry approaches that have high model capacity, such as neural nets, to really learn how to solve this problem really well. Here's a different example, on-the-fly stateless. So this example is taken from Frances Arnold's group at Caltech. Frances Arnold, if you don't know, her group works on protein engineering. And so the basic idea here is that we want to design a new protein, typically mutated from a reference protein that maximizes some function. And so the reference protein is called a parent. The mutations are called variants. By we, I mean Frances's lab. They actually synthesize the mutants. They screen them for function, such as binding affinity to a certain receptor. And from that measurement, you collect this training set, which is the input features are something based on the features, and the output measurement is something based on the functional measurement. And then we train a model, and we use that to sort of iteratively guide the next step in this optimization process. So this particular optimization process actually uses a wet lab in its cycle. And it's stateless because we don't deal with anything in the, let me just do some quick annotation. We don't deal with anything in this process. This process is considered a black box. And so we just simply put in some parameters in the beginning, which are the mutants, and we run this black box from the perspective of machine learning algorithm, a black box, and then we get an output. So this is why this is called stateless. Okay, so the key ideas here is that the data is collected on the fly. So the algorithm now has to choose what data to collect. So what mutants here to screen for. And because the data sets are relatively small in these cases, we usually train using relatively simpler models than deep neural nets. And in the simplest case, if we try to do a new protein engineering task, we actually restart this procedure from scratch. Because the models are so simple, they tend not to be able to sort of generalize across new or related problem instances. And again, we'll get deeper into this in future lectures. Okay, third example, pre-collected stateless. So the first one was pre-collected stateful. The second one was on-the-fly stateless. And this third one is pre-collected stateless. And so imagine that we have a training set of TSPs, traveling salesperson problems, or something related to a traveling salesperson problem. A traveling salesperson problem is something, or a variance of it, is something that a company like Amazon has to solve or in order to sort of do deliveries in an efficient way, or UPS or FedEx. And so this is an NP-hard problem, and there's a heuristic solver with hyperparameters that are used to solve this problem, and then it spits out a solution, right? And imagine that we are just solving a certain distribution of traveling salesperson problems, not all possible traveling salesperson problems, maybe ones that, let's say a company like Amazon may solve over and over and over again. So then we can tune the parameters of this solver on that distribution because we have training set data from it, so that at test time, when you have a new problem from the same distribution, the solver runs much faster. That's the basic idea. So we tune the hyperparameters of an existing solver on training instances. We assume the training instances are representative. We apply the tuned solver on test instances. I'll stop briefly for questions. If you have any questions, please raise your hand. Okay. So problem settings. So here we're going to start thinking about different ways of actually thinking about or breaking down learning to optimize settings that are amenable to specific classes of algorithms. And by algorithms, I mean classical algorithms. So the first one is algorithm configuration, which is basically just hyperparameter tuning. So here is just a screenshot of some of the hyperparameters of an algorithm for RNA for transcriptome assembly. And this is not, there's more that's cut off from the screenshot. And so you can see there are just a bunch of hyperparameters that we can tune for a specific set of data from a targeted domain. There's continuous optimization, such as gradient descent. So gradient descent is the workhorse of continuous optimization, and we can think about ways of learning something that looks like gradient descent but is a learned algorithm. Tree search, which is the canonical example for discrete optimization, where there's a heuristic that's trying to figure out how to navigate this search tree. So this was done, for example, in AlphaGo by DeepMind, when they had to navigate the game tree, which is a search tree, using learning to navigate that quickly to be able to find winning moves in a reasonable amount of computational time. And then the final category is predicting substructures or instantiating key subroutines of a solver. So the master solver requires a certain subroutine to identify a certain structure in the problem. And if we can use learning to predict those structures better than a handcrafted subroutine, then the solvers can run faster or better. So those are the 4 high-level categories that will make up the way that I'm going to think about decomposing topics in this class. This is not the only way to decompose topics in this research area. This is just my preferred way. So let's start with algorithm configuration. Now I'm just going to go into a little bit of detail for each of those 4 topics. We'll go into more detail later on in later lectures, but this is just to give you a flavor of the technical details for each of these topics. So algorithm configuration, also known as hyperparameter tuning in the more generic sense, although there are some interesting differences between generic hyperparameter tuning. So the basic idea is we have an algorithm. I'll just call the algorithm A. This is a classical algorithm, like an integer program solver or a tree search algorithm or what have you. It takes as input a problem instance. The algorithm has some parameters, and it outputs a solution. we assume for simplicity here that we are solving, we're going to be applying this algorithm, this solver, to a distribution of problems. Could be all the fulfillment problems that a company like Amazon might need to deal with. It could be some sort of hardware design problem, or it could be a 3D printing problem for a class of 3D printing instances that will be repeated throughout the lifetime of the 3D printer. So our goal is to tune the hyperparameters of this solver, which, you know, there could be many. Some solvers have as few as like 3 or 4. The most sophisticated solvers have hundreds of these parameters. And so we're going to tune it to optimize some objective. And the objective, it looks a lot like the stuff we see in CS155. We take the expectation over the training distribution, and we optimize some loss or cost function of our algorithm. So we assume we have training instances sampled IID from P of X. This is a standard machine learning assumption. And so the next question is, well, what is this loss function or reward function? It could be, here we're going to do minimization, so it's going to be a loss function. What is it? Here I'm plotting something that's very common in the design of these solvers, which is solution quality versus running time. So here lower is better. So solution quality is measured using a cost. So for example, the total cost of a circuit in a traveling salesperson problem. So typically a solver has this profile, which is running time versus solution quality. So how many seconds or minutes or hours you're running the solver versus what's the quality of the best solution you found so far. I left the units of the axes unlabeled on purpose because it doesn't matter for the purposes of this example. Of course, in practice, depending on whether the x-axis is seconds, minutes, or hours, or days, it changes the types of learning algorithms we want to use. If it's days, we may want to train a neural net because a neural net might take a few hours to train, but it'd be worth it. If the running time is in seconds, we may or may not want to use a neural net because training and running a neural net might just create significant overhead. But this is a typical profile that people look at when they evaluate how good a solver is. So there's a few possibilities for choosing L, capital L, this loss function or cost function. Again, everything here is phrased in terms of a minimization problem. You could also phrase it as a maximization problem, so you could phrase it as a reward function, but I'm just gonna keep it as a minimization problem for now. So here's a few possibilities. L could be the running time until finding the optimal solution. If we have a way of checking that we found the optimal solution, then L is just the running time. So we want to minimize the running time of the algorithm. L could be the quality of the best solution after a time limit, let's say 10 seconds. So what is the best solution you found after this time limit? Because I have a real-time application, it's time sensitive, I can't spend more than 10 seconds on solving this because I have to make further decisions downstream. And I just want an algorithm that is tuned to give me the best solution possible after 10 seconds. A third option is area under the curve. So if you look at, let's see, I'll open up my annotation. If you look at this guy here, the red guy, you can measure the area under this curve, which is a measure of cost, right? The smaller this area is under the curve, the lower the overall cost. So this is sort of a cost that's sort of averaged over all the running times. Whereas the green one, the green guy, let's see here. Oops, excuse me. The green guy is over here. The area is, all this stuff. My mouse disappeared. This is one of the, okay, there we go. Sorry about that. So those are just different choices of loss functions that we can plug in. Like, there's no single correct choice. It depends on your application. But these are 3 that are, I think, pretty prototypical. And you could try to minimize any of these 3 and use that as L. So here's the basic iterative procedure. We have a measurement set. I'll just call it capital S. Different papers call it different things. Initially, the measurement set is empty. The algorithm chooses a training instance, one of the problem instances in my training set. So let's say I have 1,000 instances of traveling salesperson problems. We choose a set of training instances. Capital X is a subset of the training set. Could be just one problem instance. Could be the entire training set. We choose a parameterization of the algorithm of the solver. We choose a running time limit, Tmax. Then we run our solver on this, for every problem instance that we've chosen, we run our solver on that instance with that hyperparameter until it terminates or until Tmax is reached, and then we just force the termination. We take those measurements, including the solution quality, which I'm going to call Z, just to have a completely disjoint notation so that nothing's confusing here in terms of, because sometimes people call it Y, but I use Y as the solution of the algorithm. So I'm going to call it Z here. And we add that to the measurement set, and then we repeat. We repeat from step 2 until some total time budget is exhausted, and then we have a procedure for returning the best parameter theta found so far. So that's the basic iterative procedure for hyperparameter tuning. So the design choices under this basic procedure are basically these 3 steps. How do we choose the training instances we want to measure? How do we choose the parameterizations we want to measure? And how do we choose the running time limit? So here's version 1. And I'm going to take you through just a few basic versions. Version 1, capital X is every training instance. We're going to basically whatever theta we want to measure the performance of, we want to measure it on every training instance in our training set. Here we're going to choose theta via random sampling. Just choose a theta at random from our set of possible thetas. And Tmax is infinity, so we're just going to wait until the solver finishes. Or if you can't actually do infinity, some really big number that's arbitrarily large. So this is one choice. It's perhaps the simplest possible choice. And so what are the benefits and drawbacks? Well, it's super simple. And because it's super simple, it's easy to analyze theoretically, and it's also easy to implement. Complexity of implementation is very important in practice. So things that are easier to implement are highly preferred. So it's super simple, which is a huge benefit in its own right. Of course, there are many drawbacks for something this simple. I mean, this is perhaps too simple. And the drawbacks are, well, you're doing naive trial and error on theta. So it may take you a long time to find a good theta. You're spending equal time on every training instance, which could be very wasteful because you don't want, maybe some instances are harder to learn about or estimate than other instances, but you're doing a for loop over every training instance in every round of this iterative procedure. And a large Tmax can be extremely wasteful. You could, for example, if you have one problem instance that takes you just forever to solve, then this procedure can just block on that over and over again. Okay, version 2. Capital X is again every training instance in my training set. We're going to choose theta via an algorithm in a class of algorithms known as Bayesian optimization algorithms. And again, we're going to set Tmax to be infinity or some arbitrarily large number. So this is just slightly more clever than version 1. The only difference is in step 3, where we're selecting theta using Bayesian optimization rather than completely at random. So what is Bayesian optimization? It doesn't have to be, this type of procedure doesn't have to be Bayesian, but it's commonly Bayesian. So here's the idea. We have some objective function I call it capital F. And our goal is to find a theta that max or minimizes, in this case, capital F. We can also maximize. And we assume that we can make measurements of capital F, Z. For any theta, we can measure Z, which is f of theta plus noise, under some noise model. And then the idea of Bayesian optimization, and again, we'll go into more details of this in lecture 2 on Thursday, is we have some budget, capital M. At every iteration, we choose a theta, we run f of theta, and we take a measurement, z of theta, z sub m, which is of theta, and we add that to the measurement set. And that's the basic idea. And so this is a simplification of the process that we described in the previous slide. The simplification are that, well, f here is basically the expected value of the loss function, let's say running time, or let's say best solution after 10 seconds, or area under the curve, over all the training examples. So it's averaged, it's integrated or summed over all the training examples. And we assume that the budget is atomic. So every time we measure a z, it uses 1 unit of budget. Even though some instances might be easier than others and take less time, we assume that it uses a single instance. And that's why we can reduce the previous problem, which I'll just go back to, excuse me. This previous problem says we're gonna not choose problem instances X very intelligently. In fact, we'll just choose every problem instance. And then we'll set the T max to some arbitrary large number representing infinity. And then we'll just simply focus on choosing theta under those 2 simplifications. And when we make those 2 simplifications, algorithm configuration exactly becomes a Bayesian optimization problem. And it's called Bayesian because we maintain a Bayesian belief over F. If we knew what F was exactly, we wouldn't have to measure F. We could just optimize for it directly. But the problem is that we have to make a measurement of F, which is typically expensive. And if we have a Bayesian belief over what F is, and we use that Bayesian belief to help us choose each theta, then that becomes a Bayesian optimization problem, and we'll go into details of that in lecture 2 on Thursday. But this is just the basic idea. We make these simplifications, we reduce it to a Bayesian optimization problem, or at least a canonical Bayesian optimization problem. So what are some benefits and drawbacks? Well, Bayesian optimization it's a reduction to Bayesian optimization. Bayesian optimization is well understood. Lots of algorithms for it under different assumptions, theoretical justifications, implementations of Bayesian optimization. So, once you make these 2 simplified assumptions about how you choose capital X and how you set T max, then, you can just plug and play with existing software. And we'll point you to some existing software on the course website. The drawbacks are, well, we spend equal time on every training instance because we do a for loop over every training instance every time we take a measurement, because we measure the loss function on every training instance for every time we choose a theta. And maybe we don't want to be more selective than that because some instances are easier or harder to tune than others. And again, a large Tmax can be wasteful. So those are the drawbacks. Version 3. Again, we're going to do every X as every training instance. We're not going to do anything smarter than that in the first lecture. We're going to choose theta via random sampling, and we're going to set Tmax to some arbitrary large number. We're not going to do anything smarter than that in this lecture. And now the question is, I want to focus a little bit in the version 3 on this last point, which is return the best theta found so far. So in the first 2 instances, returning the best theta found so far is basically by just statistics. We just do some empirical statistics, possibly Bayesian statistics, and we have a statistical estimate of what is the best theta found so far. If theta is a gigantic high-dimensional space, and you think you can learn a feature representation that can sort of generalize across many thetas, which is typically what people do in supervised learning, then version 3 basically reduces this to a supervised learning problem When we train a neural net, it's in the bottom right. We train a neural net to predict the cost function z on an x and theta. Whoops. On an x and theta. And then what we do is, after we train this neural net, after collecting lots of data, so we just basically use steps 2, 3, and 4, and 2, 3, 4, 5, and 6 as just a data collection process for supervised learning. And then we basically say, okay, after we train this neural net, for any given instance x, what is the theta that minimizes the response variable of this neural net under input x? So we're basically learning a proxy of the this optimization problem and cost function with supervised learning, and then we minimize the supervised learning neural net for any given x. So the benefits is that it's a reduction. Again, it's super simple. It's a reduction to supervised learning, which we know how to do. You can just plug and play this with TensorFlow or PyTorch. An additional benefit here, which is not a benefit of the previous examples, is that we can now choose theta depending on x. The previous examples just choose the global theta for all x, for all problem instances. We just committed to that theta at test time. Now, for any test time problem instance x, we can now choose the theta depending on x. So we can for different problem instances may benefit from different hyperparameter choices, and now we can do that with this approach. The drawbacks are we need to sample a lot of thetas and x's, and again, a large Tmax can be wasteful. So those are just 3 simple versions of instantiating this basic procedure. And you may already have realized some of the big limitations of these procedures if you've been thinking about problems like this in your research or other projects. And you may already think of more clever ways of doing this. And again, we'll explore more clever ways of doing this later in this class. There's many papers that are much more clever than things I described, but this just gives you a taste of the types of algorithms that we'll be studying in this space. Here's some empirical results of an approach called SMAC, sequential model-based algorithm configuration. So here, lower is better. Here, this is on a bunch of different optimization problems. And you can see that SMAC is able to, especially on the CPLEX problem, what CPLEX is an integer program solver, the CPLEX problem on the right one, it does much better than the other hyperparameter tuning algorithms. So just to give you a sense of the empirical results. I'll pause briefly if there are any questions. Okay, oops. So the next problem setting I'm going to go over, and the next few I'm going to go over a little bit faster, is the next one is going to be continuous optimization, of which gradient descent is a prototypical example. And so just a prelude. So some of the more advanced topics in this class will require some knowledge, at least a working understanding of policy learning, such as reinforcement learning and imitation learning. And so the one slide, this summary of reinforcement learning and imitation learning, is that it characterizes a stateful sequential decision-making procedure. So you have the environment of the world. In this case, it's the optimization problem. And we have an agent, which is this solver, like a tree search or a gradient descent solver, that's trying to navigate the optimization landscape of this optimization problem. The environment gives a state to the agent. This is the standard reinforcement learning lingo. The state could be the current intermediate solution of this optimization problem. The state takes an action, a local update to the current solution, and then we repeat. Give you a new state. The optimization problem gives you a new state. The goal is to, from this procedure, find an optimal policy. And imitation and reinforcement learning differ insofar as the loss function or the objective function is different. So one of them has demonstrations, such as from a pre-existing solver that we're simply trying to imitate. In reinforcement learning, we have direct measurements of the environmental reward, which is how well you're actually solving the optimization problem. and we optimize the environmental reward. So this is basically a learning-based approach or paradigm for sequential decision-making. And in this class, we often don't need this full reinforcement learning or imitation learning perspective for learning to optimize. But sometimes we do. So just to put that out there. So we can think of optimization as sequential decision-making. Many solvers are sequential. Tree search algorithms are sequential decision-making, local sequential decision-making procedures. The greedy algorithm is a local sequential decision-making procedure. Gradient descent is a local sequential decision-making procedure. So we can treat these solvers as an agent or a policy, where a state is some current or intermediate solution, and the goal is to find a state with high reward, such as a low cost or a solution to an integer program. In other words, we're trying, rather than handcrafting this local decision-making procedure, let's try to learn a local decision-making procedure. Is there a question? If there's not a question, please mute. Let's do that. Okay. So let's do continuous optimization first. So gradient descent as an agent or a policy. So we have a current or intermediate solution. I'll call it theta. That's the current state, if you will. That's the state of the agent. We have a description of an optimization problem. I'll call that X. And a gradient descent is basically a handcrafted policy. And so I wrote that there. So H, our policy, our gradient descent policy that's handcrafted, takes as input a description of the optimization problem and the current solution, and it predicts a local update, which is, I just wrote down the gradient with a step size eta. So gradient descent is a handcrafted policy. But gradient descent can be slow. It can be slow to converge. As people try different versions of it, ones with momentum, ones with other things going on. And one question is, well, okay, if we're going to be solving sort of a certain distribution of optimization problems over and over and over and over again, and we have a training set of these optimization problems, can we learn a better local update rule so that at test time, when we have to solve this optimization problem again from this distribution, we could solve it much faster? So that's the basic idea. And so I'm going to briefly summarize two papers in this space. The first one is Learning to Learn by Gradient Descent by Gradient Descent. The authors are very clever with this name. If you're interested, you can click on the link at the bottom. By the way, if you haven't already, the slides in PDF form are available off the course website right now. So you can download these slides right now. So the basic idea is their application is they have a neural net that they want to train. And gradient descent, let's say, is too slow. And so they actually use a smaller neural net to learn a local decision-making procedure to quickly train a bigger neural net, at deployment time. So there's two deployment times. So normally in deployment time, you train a neural net and then you deploy it to make tests. You can imagine a two-phase deployment time where I want to train a new neural net quickly for a new application. And I want to learn an optimizer that can solve that neural net learning problem very quickly for a class of neural net learning problems. And so the optimizer, that's a small neural net, which is our replacement for gradient descent. And yet this big optimization problem, which is basically the standard supervised learning problem of a large neural net. That's the way this particular paper is framing this problem. Of course, their optimization problem could be anything. Any kind of continuous optimization problem. In this case, it just happens to be the supervised learning optimization problem of a large neural net. And so one way to frame it is as follows. We have an overall loss. So this is the loss of the parent optimization problem for input instance X. And we have an optimization procedure. I'll call that theta sub H. That's the optimization procedure that takes as input a description of the optimization problem, X, an initial starting point, theta naught, so how you initialize the parameters, or your state, if you will, and then how many steps to run the optimization procedures. For example, if normally you run gradient descent for a million steps or 1,000 epochs or however long it is, Tmax is just that number of steps. Of course, it depends on your batch size and things like that in normal gradient descent. And so the update rules is the second bullet point. We have an H that makes a local perturbation to the current state. In gradient descent, H is handcrafted to be negative eta times the gradient of L. So, but now we want to learn H as a small neural net. And I'm not going to go into the details, but it turns out that if you set the problem correctly, you can make this whole thing fully differentiable from the parent loss function to this optimizer H. And I'll just refer to the paper for details. I don't want to go into it in this lecture. We'll cover some of these more in week 2. And so here are just some empirical results. Lower is better, and LSTM is their approach. Their model class for the gradient solver, the local optimizer, is an LSTM. And Tmax was set to 100 steps, and I forget the batch size, but it's 100 steps subject to a certain batch size. And now they're comparing against other solvers, and you can see that at least measured with number of steps, their approach is faster. Oops, sorry. One thing that's interesting, and this is something that's will come up over and over again in some of the problems that we'll be talking about, is that in this particular case, their LSTM, their Tmax is set to 100. And then in the right plot, they're actually setting the Tmax at test time to 200. So they want to actually run their solver, even though it was only trained to run for 100 steps. They're running it for 200 steps, which is outside of the training distribution. And this is an interesting experiment where they show that, well, okay, it can actually generalize to longer horizons of local gradient update, of local updates, even though it's only trained on 100. So that was an interesting finding in their paper. And then here's another experiment on a bigger data set, CFAR10, or subsets of CFAR10, CFAR5 and CFAR2, on 5 classes or 2 classes only. And what's interesting about this particular plot is the brown line, LSTM-sub. So if you look at the right plot on CFAR2, so for those of you who don't know, CFAR is an image classification data set where the input is an image and the output is one of 10 labels. And you want to train a big neural net to minimize classification accuracy, maximize classification accuracy, or minimize error or a loss function on this data set. And so typically people use gradient descent or variants of gradient descent like Atom or RMS-prop. Atom is typically the most popular ones these days. And what the brown line is showing you is that in CFAR2, they only have 2 labels. They held out, they exclude data from the other 8 labels. So and they trained the gradient optimizer. They trained the learn optimizer on a different set of 2 labels, so a completely disjoint data set. And then they tested it on training a separate set of two classes. And so there's generalization to a new data set. Of course, the data sets are related, but it's a new data set. And they showed that their learn optimizer outperforms Atom, at least measured in total number of steps of optimization. Keep in mind that these optimizers, they have different running times. So because you're running a neural net, every time you call an optimization step, each step is going to be a little bit slower than something like Atom, which doesn't need to do that necessarily. But if you just, in terms of measured by total number of steps rather than the total running time, it's faster. The calculus becomes a little bit more complicated if you're measuring wall clock running time. So I'll pause here briefly if there are any questions. Okay. So the next paper I'll briefly cover in this continuous optimization space is iterative amortized inference. So this is work by one of the TAs in this class, Joe Marino. And so first, let me describe the term amortized optimization. So amortized optimization refers to using learning to be able to predict the solution of an optimization problem. So we have an optimization problem, we solve it, and then we learn how to predict the solution of that optimization problem. So this is popularized by amortized variational inference for variational autoencoders, where a neural net known as the encoder network is actually learning to predict the solution of a variational inference procedure, which a variational inference is a very popular optimization procedure for doing probabilistic inference in deep generative models. So this can be thought of, amortized optimization can be thought of as solving this optimization problem that we described in the previous slides, where we set Tmax equal to 1. So we only want to run the optimizer for one step, and we train a neural net to be able to predict in one step as close to the optimal solution as possible. Even though it's quite popular, there are many cases where this is undesirable. The benefit, of course, is it's super fast. Just doing one forward pass of a neural net is really fast compared to like running like, you know, a million steps of gradient descent. But there's this thing called an amortization gap. And so in the bottom figure, you see in blue gradient descent of a two-dimensional optimization problem. In the red star is the global maximum. And in the turquoise diamond, it's the prediction of an amortized model that learned to predict the solution in one shot. And it does pretty well, but you see that there's a gap, and gradient descent ultimately does better, but it takes longer. And so there's a gap, if you will, there. And so what Joe worked on is this thing called iterative amortized optimization, or in the context of variational inference, iterative amortized inference. And so again, we're going to make Tmax longer than 1. Let's say we can make it 10 or 20 or 50 or whatever you want it to be. And we'll do this. We'll train a neural net to make these local update rules and just make a few, more than one, that quickly gets to something very close to the optimal solution and basically eliminates the amortization gap. And the thing that I'll just highlight in contrast to the previous thing I talked about, which is learning to learn by gradient descent by gradient descent, is that the form of H is a little bit different in Joe's work. So the circle with the dot in the second bullet point is the component-wise product. So let's say theta is, you know, a 100-dimensional vector. The circle dot is the component element-wise product. So H1 is what's called a masking policy. So H1 and H2 both take as input x, the current theta, and the gradient of the loss function. So H1 is a gating policy. It outputs a number between 0 and 1. And H2 is your update policy that predicts a new location. So there's certain reasons why this form may be desirable. And basically it says, you know, if I think for certain directions, I think right now I want to stay where I am. And for other directions, I'll just go along the direction of what H2 predicts. That's the basic idea. And so this allows you to this basically decouples the prediction of a step size, element-wise, with the prediction of a direction. And again, there's a way to integrate both H1 and H2 to make this whole thing fully differentiable from L to H. And you can see the paper for details. And we'll talk about some of these next week. Okay, some empirical results. So here's just a description of how the algorithm is running in terms of a simple two-dimensional optimization problem. So here in about less than 10 steps of running the this iterative procedure where the neural net, this pair of neural nets is predicting the optimization, we see that we've basically closed the amortization gap. We hit the global optimal solution in this particular simple example. And then in the bottom right plot, you see a curve, which is number of inference iterations. The blue line is the learned model. And you can see that it basically nails the optimal solution after just a few iterations, like less than 10, significantly less than 10. So even though you know, these normal gradient descent algorithms, handcrafted, like gradient descent, Atom, RMS prop, even though they might be on a per iteration faster than iterative this neural net that's predicting these local updates, because the neural net converges so quickly in just a few update steps, overall this is way faster than gradient descent. I'll pause briefly if there are any questions. Yes.
I have a quick question.
Yes.
So we just were talking in terms of number of iteration steps that we take. In terms of wall clock time, what are the actual benefits of training a whole nother neural net on top of the one that you're training? Because it might be too expensive. Why don't we see more people using these methods in practice? Are they just too new?
Great question. Please mute. Okay, great question. So first of all, I'll have two. There's sort of two questions in there. One is why don't we see people use this in practice? And the second one is this seems too expensive to train. So I'll answer the second question first. Is this seems too expensive to train? And here's why it may not be, depending on your application. So we assume that we have a distribution of optimization problems that we want to solve. So for example, let's say I'm a large company like Google, and I'm providing a service to small companies, where the small company says, I have my own image data set, and I want to train a neural net on my image data set very quickly. And then Google says, great, I've actually used learning to learn an optimizer for training neural nets for image classification. So then I can learn an optimizer that can optimize for your small business very quickly for your custom neural net, for your custom data set. The learning of that optimizer happens offline. So there's this offline learning procedure that learns this neural net to try to optimize well for this family of optimization problems. And then at test time, you get a single instance of this optimization problem. Let's say I'm a small business that's training my own neural net for the first time. And now I have a custom learned optimizer that learns much faster than gradient descent. So the measurement of time should be at test time, not training time. That's why this is called amortized optimization, by the way. Amortized optimization basically means that we are paying upfront. So we are paying upfront in terms of time spent to learn something, so that at test time we do something much faster. That's the hallmark of an amortization procedure. The second question you have, and of course this is reliant on having a training set. You have to have a training set of representative optimization problems that you can train an amortized optimizer upfront before you run on a test instance. So that trade-off may or may not be worth it depending on your application. If you're only going to train a neural net once, this whole procedure doesn't make any sense. If you're a company like Google that is providing a service to 100,000 small businesses, and each small business wants to train their own neural net very quickly, then you may want to pre-train your optimizer on a family of learning problems and give that to all the small businesses so that at deployment time for them, it's much faster. Now the question is, why aren't these things used? And the answer is they actually are used. So in the context of probabilistic inference, where probabilities, where the inference problem compiles to an optimization problem, and you have to run the inference procedure at test time for a new set of measurements of your phenomenon that you're modeling, people use amortized variational inference all the time. So it's used, yeah, it's basically, and so that's not everything. You know, that's just one optimization domain. And so I have a feeling that, you know, it'll just be a matter of time before other domains start using these type of approaches more commonly. And part of that comes in understanding the trade-offs. So for example, it turns out that in probabilistic inference, such as variational inference, learning this gradient descent, learning this local update rule converges very quickly after less than 10 steps, even though it takes you know, gradient descent, you know, hundreds of steps. So so at test time, it's also true that each iteration is more expensive because you have to do a forward pass of a neural net to compute your update rule. In addition to the gradient of the parent optimization problem. So each iteration is slower, and it makes sense when the number of iterations you need is way fewer than SGDs. SGD needs to be like, you know, SGD in this case, excuse me, since it's, you know, it hasn't really even converged after 300 steps, SGD may need to be like 100 times faster than calling this neural net in order for this to be worth it. In order for the neural net to not be worth it. And recall that in iterative amortized inference, which is very popular, Tmax equals 1. So when Tmax equals 1, then you're just running this neural net once. You do a one-shot prediction of the solution of this optimization problem. And in Joe's work, iterative inference, Tmax is typically like 10. Any other questions?
Yeah. So, it looks like a pretty clear application would be to use the iterative, like variational autoencoder plus SGD, because the SGD would find the optimal solution for sure, while the amortized optimizer still might not. So, are there applications where you have combined applications?
Great, thank you. Please mute. Yes, there's a paper called Semi-Amortized Variational Autoencoders. It's linked to off the course website that does exactly what you're saying. And in particular, you can think of the neural net as learning a preconditioner or learning some kind of approximate solution, and then you can use a different solver like gradient descent to fine-tune that solution. So people have suggested that. And the trade-off between whether that's better or Joe's work on iterative amortized inference is better really depends on your application. It's not well understood when one is better than the other. But that's definitely something that one can explore. So we do a one-shot prediction or just a few-shot prediction using a neural net, and then we fine-tune using something like gradient descent. Okay, in interest of time, I'm going to move on. So I'm going to go through the last two pretty quickly. So the next category is discrete optimization for tree search. Oops. And again, we're going to go back to reinforcement learning and imitation learning as sort of a way of thinking about how to learn these solvers. I guess I'll skip these. So search algorithms for discrete optimization, things include like A-star search, branch and bound, iterative deepening, and several others. Again, these can be viewed as agents or policies making local decisions. The discrete nature of these problems makes it harder to do fully differentiable learning. So you need to more leverage imitation learning and reinforcement learning to properly do learning in these settings. So a canonical example is minimum vertex cover. If you've ever seen integer programs, if you haven't, don't worry. We'll go into them in more detail in the future lectures. But minimum vertex cover is basically given a graph, find a small set of vertices that cover all the edges. And in these, and you can bring it as an integer program in the middle, where each xi is a variable, in this case binary, either 0 or 1, so it's discrete. It cannot be a real value between 0 and 1. A state is a partial assignment, is an assignment possibly partial of the integer variables, and want to find a state that's fully assigned with low cost or high reward. I think in the interest of time, I'm going to skip the description of integer programs. Well, again, we'll review these in week 2. Because I'm running a little bit behind schedule, I'm going to skip these. Again, I'll review this in week 2. And the high-level idea is that we're doing this discrete search process through a combinatorial space. And people write search heuristics. And so the question is, how do I learn to make good local decisions? And so there are many papers that do this. All of these are linked to from the course website. And so I'll just present one quick result. So this is a work by Jialin, the primary TA of the class. So in this case, we're comparing, it's an integer program, mixed integer program, and Gurubi is a commercial integer program solver. And there's a budget in terms of the size of the unique solutions that we search, unique states that we search in the search tree. And so under that measurement, we see that a learned local search approach does better. And again, I want to come back to the previous question that was raised, which is total running time. So this is a measurement on the search time. So the way we measure running time is every time you visit a new partial solution or state in the search tree, that's a budget. And in this particular experiment, the budget is 2,000. And under accounting that budget, our approach does better. So what that means is that our approach finds a good solution with fewer steps of the search tree. That does not mean that our approach is overall in wall clock time faster than Gurubi necessarily, because Gurubi might, even though it has a bigger search tree, it might search it much faster because it doesn't need to run a neural net forward pass 2,000 times in this case every time it needs to make a local decision. So there's this trade-off here in terms of how many steps of local decisions you need to find a good solution versus how long you take or how long you spend before you make a local decision. And we'll get into this in more detail later on. Any questions? Okay, so I'm going to a brief aside, choice of model class. So far, we've only discussed the learning procedure, right? We've discussed how do we set the learning problem, how do we think about the measurements, is it supervised learning, is it active learning or Bayesian optimization, is it reinforcement learning, what's the reward function, what's the loss function. We haven't yet talked about the choice of model class, which is of course also very important in getting these things to work in practice. So some common ones that people use, and again, these are things that are going to be less emphasized in this class in terms of the lectures that we're going to talk about, but there are certain things they're all in the details in the papers, in the reference papers in the class, and they're important details that one needs to address in order to do these problems well in practice. They're just for the purposes of this class less intellectually interesting, but it's important to acknowledge that these are important decisions. So common ones are graph neural nets. Graph neural nets are very popular for things that look like graphs. So mixed integer linear programs, the graphs are the integer variables and their constraints. So, graph optimization problems, these all can be solved well using graph neural nets. So the model class is instantiated using a graph neural net. If you're doing sequential optimization, you want to keep history. So if you want to implicitly learn let's say a momentum term implicitly, you could use a recurrent neural net like an LSTM for sequential decision making. If you're doing perception, so your problem requires you to process pixels for some reason, you can use a convolutional neural net. If you want to use a simpler model and you want to figure out where to collect measurements, so like in the algorithm configuration problem, you typically, or one common thing is to use Gaussian processes, which is a Bayesian approach. And the uncertainty is useful because it allows you to reason about where is the most useful informative data to collect on the fly. when you only have a limited amount of budget in terms of collecting measurements. The first three examples are cases where you have a lot of data collected up front. And then, of course, a lot of people use XGBoost because, when you're prototyping these methods, XGBoost is much faster to train than, graph neural nets, let's say. And so when you're just prototyping these methods, sometimes you just want to use XGBoost because it's just so fast, as many of you probably realized from CS155 Calico competition. Okay, so the final thing, and I'll just spend a couple minutes on this, is predicting substructures. So many solvers are actually very fast. So I keep coming back to this over and over again in terms of the empirical settings, because even though you might be faster in terms of number of iterations, unless your number of iterations you're taking is way fewer than the number of iterations of a reference solver, the reference solver can still be faster in wall clock time, which is ultimately the only thing you care about. And that's because these solvers have a bunch of heuristics. They use more than just one heuristic, and they have optimized, let's say, C code or even Fortran code in some cases. But these solvers, they can be reliant on key properties of the problem. So as soon as those properties aren't satisfied, the solvers can break down in their computational speed very quickly. And there's sort of at a high level 2 paradigms. The first paradigm is the solver needs a subroutine that can predict a few key variables that are hard. So for example, a canonical one are what are called backdoor variables, where these are the variables that if you set them first, then you can quickly determine if the remaining how to set the remaining variables. And so the reason why you want to do this is if you can predict which variables are backdoor, then you order the way you order your search problem. So you always set the backdoor variables first. So you only set them a few times. Whereas if you set the backdoor variables last, you get this exponential blow up because you're setting them an exponential number of times. So that's paradigm number 1. Can we predict backdoor variables? Can we learn to predict backdoor variables? Typically, people use various heuristics to try to identify backdoor variables. Paradigm number 2 is predicting decomposition. If we know that the solvers start breaking down after a certain problem size, maybe all we need to do is decompose the problem into smaller problems, run the solver on all the smaller problems, and then stitch the solution together in some way. And so if the solver is guaranteed to be fast, or you have high confidence can be fast for a certain class of size, then this is a good approach. And then learning here is predicting the decomposition or partitioning of the problem. And so I'll just talk about the second paradigm, just one slide. One example is called large neighborhood search. We use learning to partition all the variables, or any procedure to partition all the variables into a partitioning. We freeze all the variables except for one partition at a time, and then we run the solver on those free variables, holding all the other variables fixed, and we repeat. And the learning problem is learning to predict the partitioning. The benefits is that you leverage state-of-the-art solvers and their implementations. Can be competitive in wall clock time off the bat. You don't have to do fancy tuning or optimization of the software yourself. The drawbacks, of course, it's very reliant on an existing solver being good for a subproblem and being able to find those subproblems. So being able to learn to predict such a partitioning. So here's just some quick empirical results. This is the last slide. We have on the x-axis a wall clock time, not number of iterations of a solver, just the thing we ultimately care about at the end, wall clock time. On the y-axis, some objective, lower is better. And you see that the large neighborhood search approaches, let's say the green line, which is, or let's say the orange and the green line using learning, are very fast and are beat a commercial solver in wall clock time. And again, the neural net here is learning to predict the partitioning of the problem into subproblems. And then we actually run Gurubi on those subproblems. And then we stitch the solution back together compared to just running Gurubi on the whole problem all at once. Oops. So those are the 4 problem settings. I'm basically done with my overview. In the next lecture, we'll be doing a deeper dive into things like Bayesian optimization, a related paradigm called bandits, and looking at their application to algorithm configuration and engineering design. I'm happy to stick around for a couple minutes if anyone has any questions, but if you need to sign off now, that's totally fine. Okay, see everyone on Thursday.